So it is a real pleasure to have Professor Alisa Bokulich here to give a talk that is part of a book in progress that she's working on, and measuring the Earth and reconstructing deep time, philosophical issues in data modeling and uncertainty. And today she's going to be talking to us about the geodetic and meteorological roots of C.S. Peirce's pragmatism. So
Great.
Please welcome Alisa.
Great, thank you so much, Jackie. And thank you all for coming, and thank you, Chris, and thanks for the amazing team of graduate students who are making this all happen with awesome tech. Woo! Fabulous. All right, so this is going to be a little bit more of a historical talk, or an integrated HPS talk. And I'm going to take us back to the beginning of pragmatism, the founder of American Pragmatist School, Charles Sanders Peirce. And then we're going to go back even just a little bit further to try to figure out, where did Peirce's pragmatism come from? What were some of the sources of inspiration for his pragmatism? So there are many different things that we could highlight, but what I'm interested in tracing today is how his work as a practicing scientist, in particular his work as a geodicist, which is a subfield of the geosciences, which I'll explain in a moment, influenced his pragmatism. And I was surprised that reading lots of books about Peirce, people never mentioned the fact that he was a practicing geodicist for almost from when he graduated college to his death. So it was something that was very important to him. Geodesy and metrology, the science of measurement, were very closely intertwined. I'll talk a little bit about that. And I'll argue that they are indeed a critical but underappreciated source of influence for his pragmatic philosophy. I'm going to try to make this case with three threads or themes from his pragmatic philosophy. Each of these could be a talk unto themselves, but I'm going to try to just give an overview to try to convince you of the real richness and continuing relevance of Peirce's pragmatism for philosophy of science today. So let's get started then. So I'll start by talking about his social epistemology. I'll explain what geodesy and metrology are and what work Peirce did in those fields. We'll then connect those two things, tracing the roots of his social epistemology to that work. Second, we'll turn to the second theme of fallibilism, which he combines somewhat uniquely with a kind of realism, and I'll focus specifically on his philosophy of data, since my own interest is there. Then I'll turn to two elements of that, his error correction and dynamical view of accuracy, and what I call an adequacy for purpose view of his. And then we'll look at the legacy of his work in philosophy of metrology for today, what I see as a continuing Peircean influence in these fields. Okay, so first of all, what is social epistemology? So the dominant trend in the history of epistemology has traditionally been focused on the individual as the source of knowledge, their beliefs, their ideas, their justification. This is supposed to be the locus of knowledge production. But social epistemology, by contrast, locates knowledge production in a community of inquirers. That is, their social interactions, their norms, various institutions, as being what's important for how knowledge succeeds. Now, although social epistemology is sometimes portrayed as only having emerged relatively recently, and indeed as sort of an alternative to an anti-realist social constructivism or sociology of knowledge, this is sort of what's portrayed by Kaylin O'Connor in her step entry, for example, it in fact has a much older history in the work of Charles Sanders Peirce. So when Peirce is defending his social epistemology, he does so by contrasting it with Descartes' view, Cartesianism. I'm not worried about whether his view of Descartes is accurate or not, but let's just focus on his contrast here. So he says we can't begin with complete doubt. Doubt has to be genuine. It has to be what he calls a generative doubt. We must begin with whatever prejudices, misconceptions, biases we have. We're always going to be starting from that situation to begin with. He says to make single individuals the judges of truth is most pernicious. We individually cannot reasonably hope to obtain the ultimate philosophy which we pursue. We can only seek it as a community of philosophers. And he says reasoning and philosophy and the sciences should not form a chain of reasoning, which is no stronger than the weakest link, but rather he gives us this wonderful metaphor of a cable whose fibers are thin and tender, but yet they're woven together in a way that becomes much stronger than a linked chain. And finally, his social epistemology is also anti-foundationalist and fabulist, which we'll also talk about in a moment. And as far as I know, I think it's the first time we actually see this expression. So this is unpublished draft of one of Peirce's reply to the necessitarians, 1891. And he actually describes it as a social theory of epistemology. Interestingly, the published version does not have this phrase in it, so you have to go to the unpublished version to see him expressing it in these terms. But I don't know why he decided not to keep that. But it describes his view nicely. So Peirce was famous as a doodler. It's wonderful going into the archives. His papers are located at Harvard, which is just across the river from me at BU. So I spent lots of time there digging through his papers, and you find all these wonderful little cartoons on the side. But this is the insect metaphor. So he says the scientific world is like a colony of insects. The individual strives to produce that which he himself cannot hope to enjoy. One generation collects the premises in order that a distant generation may discover what they mean. So he really has this idea of this collective endeavor that we're engaging in that goes beyond what any one individual scientist does. So he also contrasts the definition of science, which is one that you often hear today even, that science is systematized knowledge. He attributes this to Samuel Taylor Coleridge, against whom Whewell introduced the term scientist, if you know that story. And instead, Peirce says science is instead a mode of life, right? So he doesn't want to think of it as a body of systematized knowledge, but science is a mode of life whose single animating purpose is to find out the truth, pursue this purpose with well-considered method. Scientific results are ascertained by others, seek cooperation, and will actually be developed by those who come. And he says it makes no difference how imperfect that knowledge is, how mixed with error or prejudice. From the moment that he engages in this spirit of inquiry described, that which occupies him is science. And so we have this much more sort of a processual view that science is engaged with this intention, with this process, with a community of inquirers, rather than some set of statements or theories or laws or so forth. Okay. So, again, we see him articulating the social theory of epistemology. The most vital factor, he says, to the method of modern science. He says there's these moral factors. I won't talk about his agapism today. But he says the next most vital factor is the fact that it's been made social. On one hand, scientific man recognizes as a fact of science, it must be open to anyone to observe. That's a very narrow notion of social. But he says, on the other hand, the method of modern science is social with respect to the solidarity of its efforts. And then he says the scientific specialists, the pendulum swingers and the like, are doing great and useful work, each one very little, but altogether something fast. And if you read across this in his philosophical work, you might be wondering, who are these pendulum swingers that he's referring to in this context? These are the geodesists, who are making ultra-high precision measurements of variations in Earth's gravity with pendulum gravimeters in order to determine the shape of the Earth. So I'll give you a little bit of introduction into what is geodesy. So geodesy is the science of accurately measuring and understanding Earth's geometric shape, its orientation in space, and its gravity field. Geodesy is fundamental to mapping, navigation, engineering, and the basic question of the figure of the Earth. Although we traditionally think of the Earth as this nice sphere, it's of course an oblate spheroid, but that too is an idealization, and in fact, it's much closer to this very lopsided looking thing over here, which is the geoid. So the geoid is a gravitational equipotential surface that is everywhere perpendicular to the force of gravity. If you want to try to understand this intuitively, it's the shape that an ocean surface would take if it were under the force of gravity and Earth's rotation alone. So that's where it would settle to not flowing in any direction, okay, by gravitational equipotential surface. So it results from the uneven distribution of mass and is determinable only through extensive gravity measurements and calculations. So there are two primary methods for measuring gravity in geodesy at this time. The first one is the one we just described, the pendulum measurements. Here we have a Repsol-Bessel pendulum to measure gravity, how it varies with latitude. And the alternative method was actually measuring differences in the length of meridian arcs. So if you've heard of the Great Indian Trigonometric Survey, they were involved in using these theodolites. And these were two different ways of trying to measure the shape of the Earth, the flatness of the Earth, how squashed it was. And what's interesting is that these two measurement methods did not agree. So here we have 1750, here's 1950. The light gray circles are the theodolite arc measurements. The dark black circles are the gravity measurements, and they're all over the place, right? So you see they're not agreeing with each other. They don't agree with themselves over time. But eventually we see that this scatter starts to sort of converge around this sort of 298 near the 300 mark over time. It still kind of fluctuates, but we sort of see this gradual convergence. But it's over, 200 years of time, right? It takes a long time for this to happen. And Miguel Onizorg, who recently graduated from Cambridge University HPS department, his dissertation, there's 2 wonderful papers that just came out of it recently, How Incoherent Measurement Succeeds and Pluralizing Measurement. He talks about the story of how this was resolved over time, how it was successful even though there wasn't a convergence of methods, and also how it was that by pluralizing measurement, by getting more than just these 2 methods, that's how they were able to get more accurate measurements in the long run. So I recommend those papers. How does this relate to Peirce? Well, Peirce is one of these people who are making gravity measurements. He was in charge of the pendulum measurements at the US Coast and Geodetic Survey, which was the first scientific institution in the US. And he's coming in right about here, trying to make these pendulum measurements. So this is the scientific context that fresh out of college, as soon as he graduated from Harvard, he enlists as a temporary aide in the US Coast Survey. Soon after, he becomes the second in command, and then eventually in charge of all pendulum measurements. And so he's really somebody who's concerned with this problem of how do we improve the precision and accuracy of these pendulum measurements of gravity over time, given that they have this very troubled history. So I don't have time to walk you through all of this. This is supposed to be an impression of just how detailed Peirce's contributions are to geodesy and metrology. As I said, 1859, he joins the US Coast Survey. 1867, promoted to second in command. I should mention that US Coast and Geodetic Survey is, as I said, the first scientific institution in the US. It housed within it the Office of Weights and Measures. And it was only later that that Office of Weights and Measures separated out of the Geodetic Survey, becoming the National Bureau of Standards and eventually NIST that we know today. So, and actually Peirce was somebody who was very influential in arguing that the US needed a separate Office of Weights and Measures that was independent of the Geodetic Survey. So this is just a little bit of a timeline. He was forced to resign at some point due to personality and politics. But he continues to work on it and makes contributions. And in fact, this is a manuscript in his papers in 1914 where he's still working on it just like weeks before he passed away. Okay, good. So Peirce recognized that progress in geodesy was possible only through a careful coordination of an international community of acquirers, all checking each other's measurements and trying to link them or integrate them together into a coherent and consistent whole that could be used to determine the shape of the Earth. He understood this as a limit of an iterative process of error correction and through a triangulation of different methods. And so this really helped shape his thinking about how knowledge is produced. This is his scientific report. So US Coast, he was responsible for sending in these reports to his scientific supervisor. But of course, they're sprinkled with all sorts of wonderful pragmatic philosophy. And so by looking at his scientific writings, you can glean lots of important insights that help you sort of interpret his regular philosophical writings. So he says the value of gravity determination depends on their being bound together, each with the other, right? We're trying to determine the shape of the Earth, right? You need this huge coordination project to start to bring those different numbers together. And he says at the meeting of the International Geodetic Congress in 1875, this was the year of the Meter Convention, by the way, it was resolved at the suggestion of the writer, that is Peirce himself, that the different states should carry their pendulums to Berlin, swing them there, and this was done, so forth. And he says, this is important. The solution of a great problem requires that we don't have national exclusiveness. And he says geodesy is, when science, the most successful prosecution of which depends on international solidarity. So we also see here that Peirce is really pushing this idea that science needs to be an international collaborative endeavor, that we need to bring together, and then before everyone had their own ways of doing measurements, they had their own units. It was kind of chaotic, and he really had this idea that science requires this kind of international cooperation and solidarity. Okay. So central challenges for integrating all these measurements to actually get a value for the polar flattening. some people used yards, some people used a French measure called toises, meters. There was uncertainty about how you convert between yards and meters. Peirce made contributions here. There were different realizations of the meter. There were lack of intercalibration of instruments. So Peirce is coming on this sort of chaotic field of science and figuring out how do we bring this community together to try to solve this scientific problem. So you're trying to make very sensitive measurements of gravity variations. These measurements, the data is swamped by all of these sources of error, all of these other factors, and you're trying to detect a very sensitive signal. So he really has to engage in this very careful process of standardization, of trying to make sure that we eliminate these other sources of error that are due to people using different definitions or different conversions and things like that, and that we really need to identify the sources of error. And what's interesting is that geodesy was really the driver for the rise of metrology. So metrology is the scientific study of measurement, calibration, error, and uncertainty definitions of units of measure and standards and so forth. And what I think people don't realize is that the BIPM, the International Bureau of Weights and Measures, was actually founded by geodesists and run by geodesists. It was geodesy that was driving the establishment of the meter convention and the rise of an international metrological organization. And so here's Carlos Ibanez y Rivero, the first president of the International Committee for Weights and Measures of the BIPM, and he was also the first president of the International Association of Geodesy. So both internationally and within the US, with the US Coast Survey, we see the intertwined histories of metrology and geodesy going hand in hand. And so here he mentions this. It was from the new geodesy that precision metrology was first born. Geodesy, it can no longer continue without the help of metrology. So there's this important feedback between them. Determinations of the force of the gravity of the pendulum must have a common unit, and they must be linked together of the different nations to finally have a measurement of the globe. Okay, so really all you need to take away, this is just telling some of the intertwined stories of some of his philosophical writings with these metrological writings. What I want you to take away is that Peirce's philosophical commitment to a social theory of epistemology was developed hand in hand with his innovative contributions to the norms and social institutions of geodesy and metrology. So the social epistemology is coming out of this need, this seen need to bring together this international community of inquirers, to establish certain standard norms and institutions to support that inquiry, and at the same time, his social epistemology is helping him guide that process. Okay, so that's how his work in geodesy and metrology influenced his social epistemology and vice versa. Let's turn now to his fallibilism. And I think it's important, you were talking, Ali, about the caricatures of the anti-realism of, and Peirce is importantly a realist. And I think people see his fallibilism and they think it's sort of an anti-realism or something else. He's really a realist. And I'm going to look just at in the connection to philosophy of data, because I think that's what is closest to his geodetic work. We'll look at the connections, in particular, those two things as I mentioned. So let's dive in. So what is fallibilism? Fallibilism is a term that Peirce himself coined. So he introduced this into our language. He says, fallibilism is the doctrine that our knowledge is never absolute, but always swims, as it were, in a continuum of uncertainty and indeterminacy. This is his definition. He goes on to say, science is not standing on a bedrock of fact, it is walking on a bog, and we can only say that the ground seems to hold for the present, and here I will stay until it gives way. Okay? So he has this fundamental commitment to knowledge never being absolute. It's always swimming in uncertainty and indeterminacy, and that it nonetheless is trying to make progress under these conditions. He's also a realist. He says, science fundamental hypothesis, that there are real things whose characters are independent of our opinions about them. Science has a wonderful triumphs in the way of settling opinion. These afford the explanation of my not doubting the method of hypothesis which it supposes, namely the realist hypothesis, right? So he's taking this pragmatic approach, right, to this realism, saying, I see no reason to doubt the hypothesis, right? And it's one that guides this community of inquiry. So he says reality is independent of what you or I or any finite number of people may think about it. Okay, so it's important to see that he really does have this commitment to realism along with his pragmatism. I think these two threads, his social epistemology and his fallibilism, come together in this quotation. He says, the pertinent causes of triumph of modern science are the considerable numbers of workers, unreserved discussions with one another, and each being fully informed about the work of their neighbor and availing themselves of that neighbor's results. Thus, in storming the stronghold of truth, one mounts upon the shoulders of another who has to ordinary apprehension failed, but has in truth succeeded by virtue of the lessons of their failure. And I hear echoes of Helen Longino's Science as Social Knowledge. This community have engaged in this rational discussion and debate. Stuart Firestein, biologist, his wonderful book, Failure, How Science Succeeds. And again, thinking of that failure as an important part of the scientific process. Okay, so let's turn specifically to this idea of data correction. As I said, gravity measurements are influenced, swamped out by all these different sources of error. So to get an accurate measurement of gravity, what you need to do is you need to identify, model, and correct for all the different sources of error. And this is what Peirce spent his day job doing, was he actually discovered new sources of error, he discovered ways to model them, he discovered corrections for them, he built new instruments. So you can think about correcting data in two different ways. One is by correcting your measurement apparatus, right, trying to improve it or shield it in some way. He's out there in the field. This is a field-based science, geodesy, right? It's not in a controlled laboratory setting. And so that's kind of important for influencing his views about the nature of science too, and his pragmatism. And to do that, oftentimes you can't shield, right? You can't isolate things, and instead you have to do it vicariously. This is, to use Norton and Suppé's term, not John Norton, the other Norton. Vicariously, which is that you model the sources of error and influence and you subtract them from the data. So we have this process of error correction. And I think this fits in nicely with some of my own work, which I developed before I knew about Peirce's work on this, which is that Peirce very much saw that data is not identical to the world, right? We can't just have this naive view that the data match the world. Rather, the definition we propose in this paper is that data is the record of a process of inquiry. You hope it's tied to the thing you're trying to measure, but it's also bringing along with it all this other stuff. And then here I have a taxonomy of the model lateness of data, building on some work of the sort of different ways that model correction, model conversion, what are broadly called model data symbiosis, how it is that data gets processed in various ways in order to make it better as evidence. Okay? So the observations had to be reduced or corrected. Obtaining good data often requires an iterative process of data correction, whereby the sources of error are identified, modeled, and subtracted. So literally, he would do this data, he'd do that, and he'd discover, oh no, there's a new source of error. He'd have to go back and reprocess the data and reprocess it again. And oh, that correction didn't work, let's try a different correction. So this was a community that was engaged in this process of error correction in the data. Okay. So what's interesting is that what emerges from this is what a different kind of conception of accuracy. And I think this is really influential for philosophy metrology today. Rather than thinking of accuracy as closeness to true value, we can't know the true value, right? We don't have access to true value. We can't measure how far away we are from the true value. If we had the true value, we wouldn't need to know that, right? So instead, what Peirce develops is what I call a dynamical view of accuracy. That is, that accuracy involves identifying the causes of errors and anomalies in measurements and correcting from them. Okay? So accuracy or truth becomes a limit concept of a temporally extended process of the identification and correction of measurement error. Okay? So we can't talk about making progress towards the true value because we don't know what the true value is, but we can reasonably talk about identifying sources of error in our measurement and correcting for those over time. Okay? In this communal process. So it's another way of thinking about trying to approach accuracy in a pragmatic way, right, given the inaccessibility. Okay. So we have this fallibilism, this error management I just talked about, the pragmatism that come together that I think can be described as a sort of adequacy for purpose view. Here Peirce says, dealing with what they do as matters of measurement, they can hardly conceive it possible that absolute truth should ever be reached, and therefore, instead of asking whether a proposition is true or false, they ask how great the error is, right? And so this idea of shifting the focus to, is the data adequate for what you want it to use it for, right? How great is the error? Does that amount of error undermine the project that you want to engage and use that data for, or is it good enough, right? Okay. All right, so let's turn to his work in the philosophy of metrology and its legacy today. So we're diving into this paper here. So in 1879, he writes a paper proposing that the meter be tied to the wavelength of light. This is really interesting because the rest of the international community is trying to just get the meter bar, a single meter bar that's carefully protected, under all these conditions at the BIPM in Sèvres, France. And he's like, you're already way behind, right? We should be tying it to the wavelength of light, which is what we finally did in the 60s. Peirce already understood what Arental and others have called the myth of the absolute accuracy of standards. So he writes, metallic bars used as standard of length more than once have been found to have changed their length in the course of years. The length of the yard of the metal bar should have undergone changes as the vicissitude of time bring to all material objects. So he understood that you can't just say, a meter is whatever the length of the prototype meter bar is, or a kilogram is whatever le grand K, the big K, it weighs, and so forth. He recognized already the imperfections of material objects, and that metrology had to confront this issue. It couldn't just sidestep it. So Peirce's solution was to tie it to the wavelength of light. Michaels and Morley talk about Peirce's work on this. I'll just point out that on this particular non-artifact standard, there's a wonderful paper by Robert Crease in Physics Today on his tying it to the wavelength of light, which I recommend if you want to read more about that. So this ties into some work that I've done on understanding holotypes, stratotypes, and measurement prototypes. Peirce's pragmatism and views in metrology have grown to be a central part of metrology today. One is this move away from the artifact standard. That's something that metrology has followed Peirce's view eventually. The last artifact standard was just redefined and retired in 2019. So that was the redefinition, and so just finally caught up with Peirce's recommendations. I think, if you look at here, the prototype kilogram was defined to be exactly no difference from the kilogram, right? So this is le grand K here. And all of his sister prototypes were doing this, right? And of course, if you say the definition of a kilogram is always exactly a kilogram, because it is the very definition, it could not be anything other than a kilogram. But anybody with a common pragmatic sense of science is going to look at this and go, that's not likely that all of them are going up and the K is staying the same. It's more likely that the prototype kilogram is losing weight. Okay, but anyway, so how can we make sense of that practice? I have a whole paper that talks about that in response to some others in other contexts too. Okay, but again, this is part of Peirce's philosophy here. Okay, so one thread of Peirce's philosophy of metrology is this understanding of the myth of the absolute accuracy artifact standards, moving away from those, figuring out how to address and distinguish that you can't just take it to be the definition. You need to have a way to evaluate the accuracy even of measurement standards that are supposedly the very definition of what that length or weight would be. The other thread that I want to follow through contemporary metrology is the project of the adjustment of the fundamental physical constants. So look, although we think of fundamental physical constants as constant, hence the name, their empirically determined values are not. Their empirically determined values have changed all throughout history. And in fact, many of them continue to be revised periodically over time. So I'll talk a little bit more about that in just a moment. But I want to sort of trace some path of influence for how Peirce's views came to be a part of what's called the CODATA project for the periodic readjustment of the values of the fundamental physical constants. So the graduate student, poor graduate students, who was sent to retrieve Peirce's papers when he died at Arisba was Victor Lenssen. And Victor Lenssen decided to abandon philosophy. They just sent him to go get a dead person's papers. No. But instead, he went into physics, and he joined the Berkeley physics department. And there he met Raymond Burge. Raymond Burge is a physicist you might not have heard of before, but hugely influential. He was responsible for the rise of the Berkeley physics department. The Berkeley physics department building is named after him. He recruited Lawrence, he recruited Oppenheimer, so he was really influential. But the thing that he was really famous for was there was this problem that the fundamental constants there were different values being used by different groups in different labs in different nations. And there were dependencies between these fundamental constants that which path you took to get the value led to completely different values. Now you can see if you're interested in high precision metrology, right? You need to make sure that everyone's using the same value for the fundamental constants. Otherwise your calculations are going to end up with different numbers just due to the fact that you're not using the same constant value. Does that make sense? Okay, good. So what Burge is engaged in is this mammoth project, right, of tackling the inconsistencies in the late 20s, 30s, 40s, 50s, of the entire constellation and of the empirically determined values of the physical constants in atomic physics. He reports this lack of consistency and this national flavor. Again, this idea that we need to internationalize science, right? We need to have this social epistemology coordinating this effort of defining the values of constants. So he says, lack of standardization undermines any attempt to compare measurement results from different researchers across different labs or in different countries. So he combed the physics literature, Burge did, looking for the various experimental determinations of the values of some physical constant. They were arrived at very different experimental methods. And then he had to figure out which values should be used, right? And which ones should be discarded as outliers. Very interesting methodological project for philosophers of science to look at too. So here's just an example. Here's recommended values of the speed of light from 1929 to 1973. So here's the measured value of the speed of light, and then they're down here, and then it's up here and over, right? So the measured value of the speed of light changed over time. Notice this is the uncertainty error bars. We're revising well outside of those. That's an interesting fact too, that even in fundamental physics, the values get revised outside of that. So obviously their uncertainty model was inadequate. Here's Burge's 1941 table. He points out some really interesting things about the experimentally measured values for the speed of light. He noticed that there was this convergence of these first 5 towards a very high value, 299,990. And so it looks like we have multiple, and we're looking at different measurements. This is the toothed wheel measurement, the rotating mirrors, electric circuits. There's all these different methods. So there's many different ways to measure the speed of light. They're not agreeing. There was a time where they did start to converge, but it was the wrong value. And then eventually it settles on a different value. And that's an interesting question. Why was it that these experimental physics measurements of the light, you expect them to be different, right, if they had different sources of error? Why were these different methods converging? So it raises interesting questions about bandwagon effect and so forth. Anyway, but this is just to show you that this is still happening. So this Burge project of periodically reassessing the values of the fundamental constants and adjusting their values is now taken on by the CODATA task force. Here is the latest 2018 values. 27 fundamental physical constants were changed. So here's the old value, and we have the new values that are outside, again, the uncertainty bounds of the previous values for all these various ones. Anytime you see exact, you know it's no longer being empirically determined, right? It's being stipulated, it's being defined to be a certain number. So that was a transition from these things being something that was empirically determined to something that was being conventionally stipulated, which is an interesting transition also. Okay, so you wouldn't know it, but my former PhD student and I, Federico Bocchi, have a paper that talks about Burge and some of this process. We're not looking at how the Peirce to lens into Burge influence that I was just talking about here. Instead, we're looking at the Burge to Thomas Kuhn going forward influence on the periodic readjustment of physical constants. It's called Kuhn's fifth law of thermodynamics, very cryptic, but given some of the comments that were made earlier by some of the other speakers, the fourth law of thermodynamics, according to Kuhn, is that an experimental apparatus never works the first time you try to run an experiment. The fifth law of thermodynamics is when you do get it working, it doesn't give the number you think it should. And so thinking about that as a part of a measurement philosophy and a philosophy of metrology. Okay. All right. So what's interesting is you can see Burge laying out a very Peircean view about this process of determining the values of fundamental constants. He sees it as ongoing and iterative project. He writes, quote, "The need is continuous since the most probable values today is not that of tomorrow. because of the never-ending progress of scientific research, right? So he has this very Peircean idea that the values we have for the fundamental constants today are no better, right? They're going to undergo revision too. We're going to identify new sources of error in our experiment. We're going to update it. We're going to find new triangulation ways of having different ways of measuring it to come. We're going to see different dependencies among the constants and so forth. So this is an iterative project that's ongoing. And indeed, it in fact is going on through the CODATA initiatives today. In addition, Burge highlights the social dimensions to this iterative project of determining the value of physical constants. He writes, quote, "There's required the unbiased cooperation of many persons situated in scientific laboratories throughout the world. Although the true value of the constant may not be determinable at any given moment of history, it should be a probable value, and more importantly, the same value must be coordinated and adopted across the entire scientific community." Okay, so we again see this idea of this international community. If we're actually going to make progress in detecting these minute effects of doing high precision measurement in physics, we need to be able to rule out the kind of inconsistencies that are rising from things like using different values of constants to focus on the ones that actually have an interesting physical cause to their influence that could lead to a new scientific discovery. Okay, so we see the influence of Peirce. I think you can trace it through Lenzen, because Lenzen was one of the few people who has ever talked about Peirce as a geodesist and metrologist. So he's the one who sort of wrote the foundation papers about it. And then it kind of got lost to philosophers, pragmatic philosophers. Very few have talked about Peirce's work in geodesy and metrology. Okay. This continues, so 1963 adjustment. Burge retires from the project, is taken up by Richard Cohn and Jesse Dimone. They do this project again as a part of a contribution to the same institution that Peirce was working for. Remember the Office of Weights and Measures that broke off to become the Bureau of Standards? So this is all part of this tradition. Cohn and Dimone write, "No one can guarantee that the evaluation of the fundamental constants at a given epoch yields the true values. Absolute truth, if these words have meaning, is beyond the realm of physics. All we can do at each time of reevaluation is to try to determine a set of values, which in the sense of least squares," Peirce was actually very influential, and Peirce's father, Benjamin Peirce, was very influential in importing the least squares method into the US scientific context, does the least violence. Thus, the greatest merit in a reevaluation of constants resides not in the numerical output of values. The prime object must always be to look for discrepancies and resolve them by finding the errors in either the theory or experiment which account for them. And so this is just a reminder of the similarity with what we hear in these quotations from what Peirce's own views are about this absolute truth not being accessible to science, but this process of error correction. Okay. All right, so conclusion. So hopefully I've started to convince you of the relevance of these elements of Peirce's pragmatic philosophy. First of all, seeing how they were influenced by his geodesy and metrology, but then also seeing how they have continued to influence the philosophy of data and philosophy of metrology today. We saw focus on a number of particular threads. First is social epistemology, which I think is, again, something that is sort of having a renaissance in philosophy of science in recent years, thanks to feminist social epistemology. The strength of science lies in its communal nature, critical dialogue, international solidarity of science, global cooperation and coordination is essential to the success of science. Second, we see Peirce arguing that science should be understood as a process rather than a set of facts. I think some people say this is really important for helping the public understand, for example, the COVID, what was happening with people changing their mind, like, oh, how is it that science could change its mind? Well, thinking of science as this process, right, would be a helpful thing for us to teach more broadly. And so he says, if we're to define science in the sense of characterizing living historic entity as such, it does not consist in knowing nor even organized knowledge as it does in diligent inquiry into truth for truth's sake, from an impulse to penetrating the reason of things. It is not knowing but the love of learning that characterizes the scientific person. So he has this view. Your problems would be greatly simplified if instead of saying you want to know the truth, you were saying simply that you want to attain a state of belief unassailable by doubt, right? And that's part of that commitment to pragmatism. And if you have reason to doubt, then that's when you're going to do something about it. Okay. We also saw his fallibilism, this idea that knowledge is never absolute, but always involves degrees of uncertainty. This is important. Again, you're never going to have all those decimal places. You're always going to have some uncertainty associated with any measurement value and limitations. But this is not cause for skepticism, according to Peirce, right? Oftentimes, that data can nonetheless be adequate for various purposes, right? We don't need those decimal places, perhaps. The dynamical view of accuracy as an iterative process of identifying and correcting sources of error. This is something that has gone into BIPM documents today. So if you read the BIPM Guide for the Uncertainty in Measurement, you will hear very Peircean ideas about how to think about accuracy and error. Also, philosophy of data today, I think, is influenced by Peirce's view. The recognition that data are the result of imperfect measurements. Data can't be identified with the world. Data processing, correction, modeling sources of error is required for data to become useful as evidence. Finally, philosophy of metrology. Myth of the absolute accuracy of artifact standards was a part of Peirce's philosophy. The periodic adjustment of fundamental constants as a social coordination of science and the iterative process of error detection and discovering the sources of those errors. Okay, so hopefully I've convinced you that Peirce's scientific work in geodesy and metrology are a critical but underappreciated source of his pragmatic philosophy, and that these elements of his philosophy have a continuing relevance, and we saw that with social epistemology, fallibilism with realism, and philosophy of data, and philosophy of metrology. Thank you.
So thanks so much. There's tons to ask about and talk about, but let me focus on one question about the dynamical view of accuracy, which I'm curious whether there's, to me it seems there's like a natural flip side, which is, do you have a theoretical understanding of the system you're using that justifies thinking that even in an idealized case, you'd be actually measuring the target quantity? So in the case of pendulums, obviously, I've looked at the earlier end of this, and so you have an argument that this is actually going to give you a measurement of surface gravity. I'm wondering how that plays into the dynamical view.
Peirce understood that very well. So he understands that there is this process. I mean, today we have language from philosophy of metrology today, right? You create an uncertainty model, a model of the measurement process, right? And you try to think about what are the causal influences that are coming in, what is the nature of the thing I'm trying to measure, what is the nature of my measuring instrument, how do they interact in various ways. So you have a model of that. From that, you can identify an uncertainty budget, right? And so you'll think about this, how each of those things could influence the error and whatever it might be, right? That system of errors that Peirce had, that long list, laundry list, and you identify that. But then you'll discover that there are new errors. And sometimes what often happens in the history of science is that as you're doing this process where you've sort of eliminated, you sort of standardize things, you've been able to identify many sources of error, you do this, you understand that the very concepts that what you thought you were measuring is not what you thought you're measuring. And then there's often a bifurcation. So in my book, another chapter talks about how the notion of height, very simple sounding concept, everyday, how could height be hard? There's actually a bifurcation of 6 different definitions of height, none of which satisfy all of our pre-theoretical intuitions about what height should do. So it's really interesting to think about how, as you increase the precision of a measurement, understand more of the sources of uncertainty error, that often pushes us to then redefine and perhaps even bifurcate concepts in various ways. And then you do it again, right? And this is part of this iterative process.
And at this point, are they worried about, so initially, like with Maupertuis, you were measuring the shape of the Earth, but at what point did they start to think of it as measuring the distribution of matter inside the Earth?
Peirce's life, right? So it's literally, he starts his beginning of his career just with the oblate sphere, measuring the polar flattening. And then by the end of his career, it's changed, right? And this is part of why I think he struggles with this question, because then the question becomes, are we trying to get these super high precision measurements where we really identify this uncertainty budget, this error model in high detail, or do we just need lots more data, right? And so there was kind of like, he was right that ultimately we should come back to that, but there was a time in which they had to sort of do cruder measurements because they were recognizing that there was going to be all of these variations due to the local differences in geology and so forth. And then discovering mountain roots and thinking how that influences the pendulum measurements, the being nearby a mountain, and of course Newton struggled with that question too. So yeah, absolutely, that was a part of the process that he experienced in his lifetime and was grappling with. Yeah, great. Thank you.
Simple question. It sounds to me a lot in common with Mach, Ernst Mach. Same. Is there a reciprocal influence of some kind? Same age, right?
Yeah. So I mean, Peirce. I haven't looked entirely into Peirce's relationship with Mach. He translated some of Mach's writings for this. He knew Mach and he worked on translating, but he kept slipping in his own views. When he would translate Mach, he was like correcting Mach on this and correcting him on that. And so I think there are differences between them that came out, but I can't give you a full story about the relationship.
Did Mach knew to your knowledge?
Did he read the English? I don't think so. So he never knew, perhaps. But yeah.
The historical part, the collective part, is a lot.
Yeah, well, of course, as we saw, Peirce is not afraid of metaphysics, and Mach, famously, there's a lot of philosophical differences between them, right? But I think they were both very philosophical physicists. Peirce was doing more geophysics, but thinking about those issues in similar ways. Yeah. Thank you.
Thanks. So my question is actually pretty similar to Chris's, but maybe just asking it a slightly different way. So this sort of dynamical view of accuracy, like I said, seems to assume that we have some preconception of what the quantities we're measuring, and we're trying to remove errors from that quantity. But then, and you mentioned that these concepts can bifurcate. Did he have much to say about how that happens or why that happens? Because that's quite relevant. At least in physics today, we have the Hubble tension.
Yeah, and
we're not sure if we're measuring the same thing. There's debates.
Yeah. So the way that Peirce talks about it is through the kind of triangulation of different measurement methods. So he talks about the different kinds of methods for measuring, let's say, the speed of light or something like that. So oftentimes it's because you have these different measurement methods that resist a convergence, right? So sometimes you can get the convergence to happen, you can identify a source of error, and they really were measuring the same thing. But sometimes it turns out that they were not. And so I think Peirce had an understanding that plural, so this is what, Miguel talks about this in this particular case, but it's a more general, we talk about triangulation, right? Of bringing multiple measurement methods together as a way of, that's when you start to see that maybe we're not actually measuring the same thing and we need to separate our concepts in various ways. Yeah, but you can only do that kind of when you reach a certain level of precision and expectation of what you ought to get, that then you start to be able to see where you need to revise things. So it's kind of part of an extended process. Yeah.
Sorry, I was inserting myself in the queue, but you can go ahead. I didn't see you over there. I'll go.
My question is regarding Peirce's idea of community of inquirers.
Yeah.
So it seems like for Peirce, only scientists are included in the community of inquirers. So can you elaborate more on who are part of this community?
Yeah, so actually Peirce thought that the scientific inquiry and philosophical inquiry was continuous. So he thought what works in science should also be what works in philosophy. So, and indeed, if you study HPS, you're like, for most of history, philosophy and science were not distinguished. It was natural philosophy, right? So I could, so he was part of, this was the time that Whewell was introducing the notion of scientists as separate from natural philosophy. We start to see this professionalization and this breaking off. But of course, for Peirce himself, he is both a philosopher and a practicing scientist. And so he's seeing this community as being much broader, and he's seeing these epistemological lessons as being ones that translate across philosophy and science. So using the same methods.
Am I allowed to?
Go ahead, you've earned it.
No, okay. So I really enjoy that a lot, and I look at neuroscience, and there are problems in neuroscience with respect to being able to kind of coordinate practices. I mean, it's different than just, it's a bit different, but I was interested in to what extent Peirce's view played a normative role in how the science was going, because was he the only one who was looking at it? Do you know this? I mean, was he the only one at the time that was looking at the fact that there was this sort of iterative, this coordination problem? And did he play a role kind of in normatively shaping how things panned out? And I apologize if I missed it in the talk.
No.
And so I guess that's where I'll stop.
No, great question. So I didn't have time to talk about it in the talk, but it is in the chapter. So there were two things. One was he was a part of this U.S. Coast and Geodetic Survey, the first scientific institution. The American science is trying to establish itself in relation to Europe, right? And so it's really trying to achieve this coordination. And so Peirce was actually one of the first representatives from a U.S. scientific institution to go abroad for a scientific meeting, which is like, how late is that? Anyway, but so it's interesting that, so he is playing an important role, but this idea of the social coordination, I mentioned the Ibanez quotation. This was something that all geodesists were struggling with. So there's a sense in which his social epistemology wasn't completely original, unique to him, but it was the scientific part of it was coming from geodesy as being the community that was really trying to do this coordination. It was sending, first of all, expeditions around the world, tapping local scientists, trying to bring these things together. So those kind of elements were already a part of sort of geodesy, but Peirce was certainly the one that was helping sort of formulate it, lead it forward. He was the one who was saying we need to also calibrate our instruments. We'll take the exact same pendulum into these different places and let's both measure that gravity at that location with our different instruments and then be able to start to detect, the different values that way. So he was very much, he was very normatively involved in that project, but he was also a part of a community that was engaged in that. But he was bringing this kind of philosophical rigor to it in a way that was helpful.
Oh,
Yeah.
Thanks so much. Oh, I'm sorry, Kim. I wasn't, I'm doing my due diligence. And then Bill.
Thanks. Really a wonderful talk.
Thank you.
Loved it. I'm teaching a seminar this semester on William James' Principles of Psychology. And we're trying to do a similar thing to see how that informed his philosophy. I'm wondering two things. One, what advice you might have for us doing a parallel thing, but also what about so James and Dewey started as psychologists. And that, Peirce in geodesy, and I'm wondering if you have any ideas about how that might account for their different philosophical views. And I noticed one of the articles of Peirce's you referred to is what is pragmatism, and isn't that where he set out this elegant term, pragmatism?
It is, yep.
And
a term ugly enough it wouldn't be stolen by the other pragmatists, right? Yeah.
And that was, as I understand it, much of it was to criticize James. And I wonder if you have any ideas about how their difference in philosophical views might have been connected to the different sciences.
Yeah, no, that's a very interesting question. So on the question of how James was influenced by psychological research, I would recommend Claudia Cristalli's work. She was, I think, a postdoc at HPS and IU, and I don't know if she has a permanent position yet, but she's a wonderful junior scholar who's actually writing on this topic. I was just at a conference with her this summer. So Cristalli, Cristalli. And so look at her work on that question. As far as I have not looked at James, I've not looked at the psychological research. I do think that there is an interesting line of influence actually from Peirce's father, Benjamin Peirce, who was doing astronomy. He was at Harvard Observatory, and he was also involved in the US Coast and Geodetic Survey and helped secure his son's position there. But anyhow, so one of the things that Benjamin Peirce was interested in was the importance of measurements in astronomy of longitude, what's called the personal equation. This idea that individual observers are getting different numbers. And there was this scandal where this junior observer was fired because he wasn't getting the right numbers as the senior scientist. But then it was realized, no, everybody gets different numbers. Everyone has a personal equation. So when you start to develop your uncertainty model, you need a new line in your uncertainty budget, your personal equation for your individual. And that idea of the individual as sort of these different observers, and I think there was some interesting research being done on the sort of individual psychology, individual differences of perception, and then what's common about perception and perception being delayed and signals taking time. And so there was kind of this evolution from this astronomy work on the personal equation to this psychological research about what's kind of universal about perception and processing of signals in the mind, and also what is unique among different observers, and how can we take account of that when we're trying to do high precision measurement in metrology.
This is not so. It was quite striking that when they realized they had to change the time standard because the rotation of the Earth was slowing down, and there were two. The first version of it tried to use what the rotation was at 1900. And it turned out, Curtis Wilson has pushed me on that. It turned out that this was enormously complicated to work through. And the change that was made later to use some atomic
Cesium atom transitions.
Sorry?
Cesium 133 for the definition of the
Yeah.
second. Yeah.
And that, now I presume it was a lot easier to coordinate.
Aaron Tull is the person you need to read on that. So he talks all about these cesium fountains and how even then, even getting it down to this really high precision context, there's questions about where are these measurements being done. If it's being done in Colorado, you have to take into account geodesy and differences of gravitation of the elevation. So even time becomes dependent on these high precision gravity measurements that Peirce is doing, because obviously it'll affect the time dilation, this position in the gravitational field. Yeah, so even the cesium atom time is dependent on these things in interesting ways. But Aaron Tull has wonderful work, not relating it to this geodesy and gravitation measurement, but on the cesium fountains that in the definition of the second. I recommend.
Chris has another question.
Please.
I'm allowed, yes.
Yeah.
He's allowed it, we gave him permission.
So there's just a really general question once you go to a social epistemology of how to think about judgment aggregation. And in this case, there's a very concrete form of that question because you're looking at measurements from a variety of different sources. And I don't know, you mentioned his father, so I know in astronomy at this time, statistical methods were being developed. So how much of Peirce's work was actually developing the statistical methodology to consider how to do judgment aggregation, and also what we now call meta-analysis, right? Sort of aggregation across different types of...
So Peirce and his father were both very influential in, as I mentioned briefly, the least squares method, but Benjamin Peirce was actually one of the first people to really sort of identify the difference between sort of random error and systematic error. And so at this time, people were thinking, random error, if you just increase the number of measurements and observations in the infinite limit, you can reduce the error completely, right? You can get to an accurate value. And Benjamin Peirce and then also Charles were arguing, no, there's actually this different category of error that can't be solved through these kind of statistical methods, namely the systematic uncertainty or systematic error. And so you really kind of see that distinction emerging at this time and them kind of pushing it in this geodetic context. And so a lot of the sources of error that Peirce is identifying are these systematic errors, not random errors. And so that was really an important part of his work. And then developing the least squares method. And then, Burge kind of is picking up when Burge is doing the readjustment of the fundamental physical constants at Berkeley, he's picking up a lot of Peirce's statistical methods of least squared analysis when he's doing it as well.
This was awesome. I love this talk so much for so many reasons. What I'd be curious to know is Chris Mink and Bill Harper have done work on like Newton's method of theory testing and George Smith, the whole closing the loop stuff.
Absolutely.
With Peirce working on the stuff that he's working on, how much was he influenced by Newton's way of dealing with kind of inaccuracy in measurement?
Yes. Okay, so there's a lot to say about that. Certainly he has this idea of this, George's closing the loop is this iterative process of identifying, seeing which ones have a physical source that they can be accounted for, and seeing. You can also relate it to another thread of tradition in the history of the philosophy of science, which is Whewell and Mill and Herschel's method of residue, and the iterative process of that as well. There's really kind of it's a complex story of a lot of these 19th century figures coming together, thinking about this process that I think influenced. I'm sorry, pointing to you because I know you collaborate with George. On this question of closing the loop. And so, Peirce is a part of that 19th century movement. And Peirce is influenced by Whewell especially. And Whewell was also working in the geosciences. So I have another chapter that talks about Whewell's tidology and how that's his philosophy of data is helping develop a lot of his views in the philosophy of science also in methodology. And Miguel Nazorg and I and my PhD student, Matilda, are working on a paper where we talk about the method of residue in that history. So that'll be out soon, hopefully.
This is slightly tangential, but it's prompted by a passing remark about the public on topics like COVID might find it much more persuasive if they were taught that science is this process rather than specific, definite results.
Mhm.
How optimistic are you actually about this?
I am the hopeless optimist that goes off the cliff. I mean, are we doing nothing, right? Or do we something that's imperfect that's better than nothing? So, I mean, I'm biased as a philosopher of science in that I do think philosophy of science has something to contribute to that conversation.
Oh,
and
huge, absolutely
and,
huge. But in a day-to-day sense, for people who hardly
yeah.
pay attention to the news, and they start hearing about Bill Gates inserting
right.
things in your
Yeah.
and
So
you're told, science is a process, not a
no, but it's a right by this important community of inquirers that are holding each other accountable and and source the error of correction and so forth. So I mean, I think you have to add all those extra caveats to it as well.
Yeah.
But I do think that would be helpful. Also, not just for the public, but I also think scientists need to learn this also. So what's really interesting about this work on the values of fundamental constants is like a lot of scientists don't seem to know this, that like all books and tables of fundamental constants. So one of the people who's involved in the periodic readjustment, Paul Taylor, says it should have a big red warning label, warning, these numbers are going to change in 4 years, be aware of it. And I actually first kind of came to know about this work on fundamental constants on my paper on calibration, coherence, and consistency in radiometric measures of geologic time. So thinking about how radiometric dating and when they're doing radiometric dating, they're depending on fundamental constant values of decay rates, and the empirically determined values of those things change over time. So if you actually want to compare different dates, you have to ask when was that calculated, those dates. And sometimes you'll need to readjust the number based on making sure that the values of the fundamental constants are the same so that they're actually commensurable to answer questions about cause and effect in the history of the Earth. So it's really important for scientists also to understand this iterative process, that even fundamental constants are going to have different values, so you can't really compare. They're not really commensurate at different times unless you do the error correction, right, for how that's changed over time. So I do think this process is something that's important for, as where philosophers can bring this to science, but also bring it to the broader public, thinking of this process of how it evolves. I'm biased.
Okay, well, let's thank Alisa for
Thank you all for